Hello students, let's talk about lecture 4.3, what derivatives tell us. I know that this is pretty much one-way communication. I'm actually going over the lectures and I help you fill it in, but do not hesitate to email me if you have questions. Email me questions about your homework problems. I am just one email away. So let's discuss 4.3. Now, please read the definitions and read carefully through these. The most important part is the test for intervals of increase and decrease. So this is the important one where we have that if f prime of x is greater than 0, so basically if we here increase and decrease, we have to connect it with the first derivative of a function. So if the first derivative of a function is positive at all interior points of some interval I, then f is increasing on I. So this is a very important sentence. If you calculate the derivative of a function and it's greater than 0 on all the points of I, then f is increasing on I. The second one is if f prime of x is less than 0 at all interior points of I, then f is decreasing on I. So very, very important. So try to do example 9 on your own. Now, let's do one example together. So example 19 says, find the intervals on which f is increasing and the intervals on which it is decreasing. So we have the function f of x equals 4 minus x squared. So as we saw before, we have to calculate the first derivative. So f prime of x is, you can pause this video and calculate the derivative on your own, is negative 2x, right? So basically, where is this function positive and where is it negative? Well, I'm going to make a table because that's easy to work on. And I'm going to put f prime of x on the second line and f of x on the third one. So on the first one is x. And I'm going to put the domain of this function, which is from negative infinity to infinity, right? Because it's a polynomial. And then the derivative of f of x is negative 2x, and the solution of negative 2x equals 0, it's actually x equals 0, right? So this function is 0 at 0. So if I put 0 here, I get 0 here. Now, choose a number to the left of 0. So let's say negative 2. What is f prime of negative 2? What is negative 2 times negative 2, which is 4? What if you calculate another one, negative 3, and so on? You're going to get positive numbers. So I'm going to put here plus. And to the right, well, let's choose 3, for example. What is f prime of 3? Well, f prime of 3 is negative 2 times 3, which is negative 6. So we have negative values here. Choose more numbers if you want to double check. So what does that mean? It means the first derivative of f, it's positive between negative infinity and 0. So the function is increasing between negative infinity and 0, and it's decreasing between 0 and infinity. So f increases on negative infinity 0, and f decreases on 0 infinity. Okay, I hope this one is helpful. Let's discuss another problem. Find the intervals on which f is increasing and the intervals on which f is decreasing. So again, we want to calculate the derivative. So f prime of x equals negative 3 sine of 3x times 3. So basically it's negative 9 sine of 3x. So what we have here is a trigonometric equation. So negative 9 sine of 3x equals 0 means sine of 3x equals 0. So trigonometric equations. So go to your trig notebook and check the trigonometric equations. So this means 3x can be what? Well, sine of what number is 0? Well, sine of 0, sine of pi, sine of 2 pi, sine of 3 pi, and so on, and also sine of negative pi, right? So basically, 3x can be equal k pi, where k, it's an integer. So basically, x equals k pi over 3. Or in our case, if k equals 0, x equals 0. If k equals 1, x equals pi over 3. K equals 2, x equals 2 pi over 3. K equals 3, x equals pi. And if k equals negative 1, so we can put plus minus, pi over 3 plus minus 2 pi over 3 and plus minus pi. So basically, find the intervals on which f is increasing and decreasing. So far what we found is the first line of our table. So x, f prime of x, and f of x. So on the first line, I'm going to put negative pi, negative 2 pi over 3, negative pi over 3, 0, pi over 3, 2 pi over 3, pi. So these are all zeros because that's how we found them. They are solutions of the first derivative. Now the question is, what signs we have between negative pi and negative 2 pi over 3? So the question is, what was f of x? F of x was defined to be 3 cosine of 3x. So the question is, if you choose a number between negative pi and negative 2 pi over 3, what kind of sign it has? Or we could actually just graph this function and see what's going on. So if we graph it, we know the amplitude is 3, the period is 2 pi over 3, and the scale is 2 pi over 12, which is pi over 6. So basically, our graph looks like this: pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, and then negative ones, negative pi over 6, negative pi over 3, negative pi over 2, negative 2 pi over 3. So it's 3 and negative 3 cosine. So we start at 3, 0, negative 1, and so on. And the same thing on the other side. So we actually figure out the signs between 0 and pi over 6. Well, if we think about it, 0 and pi over 3. So we want to find the sign of f prime of x. So we want to graph f prime of x. So how do we graph that? Well, the amplitude is 9, the period is 2 pi over 3, and the scale is the period over 4, so it's 2 pi over 12, which is pi over 6. So when we graph it, we have pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, which is 2 pi over 3. I'm going to draw one more period. So 4 pi over 6, 5 pi over 6, 6 pi over 6. Well, I think it's enough because our domain is from negative pi to pi. So then the other side, negative pi over 6, negative pi over 3, negative pi over 2, negative 2 pi over 3, negative pi, and that's enough. So 3, 9, and negative 9. Now our, I guess we can make it a little bit, we'll leave it like that. So it starts at negative 9, so 0, and then instead of going up, we go down and then up. So this is the graph on the positive side, and then the negative one, up, down. Okay, so now it's easy to see that between negative pi and negative 2 pi over 3, which is this region, our function being above the x-axis is positive, so I'm going to put plus. On between negative pi over 3 and negative pi over 3 is this green part, which is negative because it's under the x-axis. And then positive, and then negative, and then positive again, and then negative. So basically what's telling us is the function f, it's increasing. So f, it's increasing on negative pi, negative 2 pi over 3. Then it's decreasing, and then it's increasing again, decreasing, increasing, decreasing. So it's increasing on this interval union negative pi over 3, 0, and then union pi over 3, 2 pi over 3. Right, from where I got them, because it's increasing here, it's increasing, so plus, you see how it's connected between this, it's positive, and then f is decreasing on, well, negative 2 pi over 3, negative pi over 3, union 0 pi over 3, union 2 pi over 3 pi. So if I were to color code them, I would get this interval here, and this one, and this one. So the interval is between these two numbers, between these two numbers, and between these two numbers, where it decreases. Okay, let's see. So, first derivative test, very important, read it carefully. It says, if f prime changes sign from positive to negative, as x increases through c, then f has a local maximum. If f prime changes sign from negative to positive, as x increases through c, then f has a local minimum at c. What is this c? The c, it's a critical point. So the critical point, how do I find critical point? By doing the first derivative. If f prime is positive on both sides near c or negative on both sides near c, then f has no local extreme value at c. So let's do this problem. First derivative test. Let f of x equals x squared plus 3 or negative 3, 2. Locate the critical points. So f prime of x equals 2x. So if we set this equal to 0, we get x equals 0. So this is critical point. Part B, so it might be local maximum or local minimum. Now it says use the first derivative test to locate the maximum or minimum values. So we make a table, we put x, f prime, and f. So the domain is from negative 3 to 2. They gave us that here. F prime of 0 is 0. Now, if you choose a point to the left of 0, you're going to get negative values, right? This is f prime of x. So if you choose negative 1, you get negative 2. So that's why I put minus. 0, 2, if you choose 1, you get 2. So you have positive values. So what does that mean? It's decreasing and then it's increasing. So what does that mean? Well, if the function is decreasing and then it's increasing, right? It's decreasing. It looks like a valley. So this point here is going to be local minimum. And what's the locate the minimum? So we locate it. The local minimum occurs at x equals 0. I don't know the value, but I know for sure that it occurs at 0, right? That's the point here. Identify the absolute maximum and minimum values of the function when they exist. Well, if there is only one minimum for the whole function, then that's actually an absolute minimum. So part C, the absolute minimum, because it's only one, right? Absolute minimum is equal to f of 0. So basically it's 0 to the second plus 3, which is 3. And I can put here 3. Okay. Okay, now let's discuss the second part, the concavity and inflection point. So, test for concavity. Suppose f double prime exists on an open interval I. Well, concavity means when it looks like this or it looks like that. When I learned it in high school, we call it when it holds water, concave up, and when it doesn't hold water, concave down. Kind of makes sense. Suppose f double prime exists on an open interval I. If the second derivative of f is positive on I, then f is concave up on I. If the second derivative is less than 0 on I, then f is concave down. If C is a point on I at which f double prime changes sign at C from positive to negative or vice versa, then f has an inflection point. So let's discuss this example. Determine the intervals on which f of x equals x to the fourth minus 2x to the third plus 1. It's concave up or concave down. Identify any inflection points. So step 1, find the second derivative of f. So f prime of x is 4x to the third minus 6x squared. F double prime of x is 12x squared minus 6x. To find inflection points, we are going to set this. So step 2, set f double prime of x equal to 0. So 12x to the second minus 6x equals 0. It's 6x equals times 2x minus 1 equals 0, which means x equals 0 and x equals a half. So these are solutions of the second derivative. Now, we don't know exactly if they are inflection points because a point is inflection point if f double prime changes sign at x. So what we're going to do next, we're going to make that table that we usually did for the previous, for maximum and minimum. So the table is going to contain x, f double prime of x, and f of x. So in this case, I'm going to put negative infinity to positive infinity because it's a polynomial, so that's the domain, right? They didn't give us any restrictions. I'm going to put 0 and a half. Make sure you put them in the order. They are solutions, so I'm going to put 0. Now I want to find out what sign should I put in this highlighted part. Well, for that, you just pick a number between negative infinity and 0. So I'm just going to choose negative 1 and calculate f double prime of negative 1. Well, that would be 12 plus 6, 18. So here I'm going to put plus. Then I'm going to pick a number between 0 and a half. So f double prime, that 1/3. I think that's a good one. 12 times 1 over 9 minus 6 times 1/3. So if we divide by 3, we get 4 over 3 minus 2. So it's negative 2 over 3. So it's a negative. And then choose a number in this area. So I can use 5, for example, and calculate f double prime of 5. Well, f double prime of 5 is going to be positive. What does that mean? It means on this region, it holds water, so it's concave up, concave down, and concave up. What does that mean? Well, this point here, because it changes sign, and this one is changing sign, they are inflection points. So actually, 0 and 2 are inflection points. But it's not enough just to be solutions of the second derivative. They actually have to change the sign. Okay. So read through these directions and let me solve one more problem for you. It says, locate the critical points of the following function, then use the second derivative to determine whether they correspond to local maximum or minimum. Okay, so let's do f prime of x equals 3x squared minus 6x. So we set this one equal to 0 to find the critical point. So 3x squared minus 6x equals 0. It means 3x times x minus 2 equals 0. So we get 0 and we get x equals 0 and we get x equals 2. So these are critical points. They can be points of where maximum or minimum occurs. But the property above it says if double prime at c at some point, that's a solution of the first derivative, it's positive, then f has a local minimum. And does it make sense? Well, if the second derivative is positive, then it means it's concave up. So of course this point here, which is like the bottom of a hill, of a valley, is going to be a minimum. And the second derivative, it's negative, then it's concave down, so it's going to make a maximum there. And if the second derivative at point is 0, then the test is inconclusive. Okay, so let's calculate the second derivative of x, which is 6x minus 6, and then calculate f double prime at 0. So that's negative 6. So it's at what? If the second derivative is less than 0, f has a local maximum. So this is less than 0, so it means f has a local maximum, right? Because it's less than 0, so it's concave down at x equals 0. I do not know the value of the maximum, but I know if there is a local maximum. F double prime at 2, so from where I got this 0 and this 2, from the solutions of the first derivative, is 6, which is positive, so f has a local minimum at x equals 2. Why? Because being positive, it means it holds water, or it's concave up. Okay, and this, you can skip the last problem. This would be all. Have a good day.